So at our last lesson, we introduced a whole group of new classifiers. We introduced decision trees, ensembles of decision trees, and then we also looked at the support vector classifier and the maximal margin classifier. And today we're going to try and look at those, play with them a little more, and get a much better intuition for how they work. So we're going to start with decision trees. I'm going to read in this notebook of very simple toy data about various animals. So for each animal, we have some features, and then we have a class label about what type of animal they are. We're going to turn this into a binary classification problem. So now all of my labels are either mammal or non-mammal. So imagine this as a binary classification problem where we're trying to distinguish between mammals and non-mammals. Okay, so I'm going to build a decision tree using the decision tree classifier method in sklearn. I'm going to specify that we want to use an entropy method that we mentioned for splitting. So you may recall we mentioned a few different values you can use to decide what to split on. You can use a classification error, you can use a Gini index, you could use an entropy. We're going to use entropy here. And just like all the other sklearn methods, I can instantiate one, and then I just call fit and pass x and y values. Now, the tree submodule in sklearn includes a very handy feature for plotting the tree. So we're going to use it. And let's take a moment to understand this plot. Okay, so I can see the entire decision tree and every split. Within each node, it shows me what the split variable and what the cut point was for that split. So for example, at the root of the tree, I'm splitting on whether the animal gives birth or not. Right? If the animal does give birth, I'm going to follow the positive path. And if the animal does not give birth, I'll follow the negative path. Okay? This is a positive path. This is a negative path. Then I also see the entropy of the node. So this is the entropy of the entire data set. Is 0.9 a large value or a small value for entropy? Okay, that's a large value. The total range of entropy is just 0 to 1. So an entropy of 0.9 is fairly high. Then I also see that I have 15 samples that are kind of placed into this node as I go through the decision tree. And it also shows me the class breakdown of the samples. So 5 of the samples are in the first class, which is mammals, and 10 of the samples are in the second class, which is non-mammals. And therefore, if this was the last node in the tree, if it was a leaf node and I landed here, the predicted class for this node will be non-mammals, because that's the majority class. I also see that the node is colored according to the most common class. So all of the blue nodes means that non-mammals are the most common class at that node. And it's only partway blue, so it's kind of a light blue to indicate that there's still some entropy in that node. Not all of the values that fall in that node are non-mammals. So I have all of my values in here, and then I choose to split on gives birth. Okay, so looking here at the data, I can see humans give birth, whales give birth, bats give birth, cats, leopard sharks, and porcupines give birth. So those will all be follow this path into the positive gives birth side. All of the animals that do not give birth that land in here, let's look at those first. So among those animals, the entropy was 0. What does that mean? It means all of the values in this node fall into the same class. And we can indeed see there are 9 samples that fell along this path. And of those, 0 are mammals, 9 are non-mammals. And so the predicted class for this region of the feature space is going to be non-mammals. And then we stop there. We don't split again because there is no entropy at that node, so there's nothing to split. Then if we follow the other path, so if we follow the path along the animals who do give birth, you can see in this node, the entropy is 0.65. So that's lower. There were 6 samples. Of the 6 samples, 5 are mammals, 1 are non-mammals. So we could split on any variable that kind of distinguishes that one from the other 5. In this case, we chose to split on warm-blooded. Okay. So then if we look at those who are animals that give birth but are not warm-blooded, we end up in this node where there's only 1 sample, but it's a non-mammal. So the predicted class here is non-mammal. And then along this node are those who give birth and are warm-blooded, and all 5 of these are mammals. Now, we mentioned that the decision tree classifier has kind of a built-in feature that it can tell us about feature importance. Okay. So by looking at what feature is used in each split and what the reduction in entropy was due to that feature, we get a rough measure of feature importance, and the sklearn implementation can tell me that. Okay, so here we can see that warm-blooded is about 28% of the solution, and gives birth is about 71%. Does this make sense given this tree? So gives birth gave us the greatest reduction in entropy, and it applied to the most samples. Warm-blooded applied to fewer samples, but also gave us a large reduction in entropy. And none of the other features were relevant at all in this decision tree, so they all have a feature importance of 0. Now, in our lecture, we spoke about a bag tree. A bag tree is a tree where we make many copies of this data set by sampling with replacement. So currently I have 15 samples in this data set. And when I sample with replacement, let's say I'll have many data sets, all with 15 samples, but I might have duplicates of some samples and I might be missing some others. And then I'm going to train many trees, each on a different bootstrap data set, and I'll average their output, or I'll take the output of the majority vote. Okay, so let's do that. I'm going to fit a bagging classifier, and I'm going to specify that I want to use 3 trees. And now I'm going to plot all 3 of the trees. So these are the trees I came up with. So one tree is splitting on warm-blooded. And notice that I'm able to completely categorize all the samples just based on warm-blooded. But in the original tree, I was not. So let's see why. In the original data set, okay, so let's look at warm-blooded and mammals. In the original data set, is warm-blooded a perfect predictor of whether something is a mammal? Okay, in the original data set, I have 2 samples that are warm-blooded but non-mammals. So the pigeon and the penguin. All of the other samples that are warm-blooded are mammals. So in the original data set, it's not enough to just split on warm-blooded. But in the bootstrap data set, I was able to completely classify my samples just based on warm-blooded. Why? Well, let's look at the actual bootstrap data set I used. So do you see any penguin or pigeon in this data set? When we sampled with replacement, in this bootstrap data set, we happen to not sample the penguin or the pigeon. On the other hand, notice that we have 2 copies of the frog. We have 2 copies of the eel. We have a full 4 copies of the whale. Right? So our bootstrap data set is slightly different. And that's also why every tree is slightly different. Okay. So for example, this one, I can completely separate the classes based on warm-blooded. In this one, it's based on whether they give birth. In this one, it's based on first whether they're an aquatic creature and later whether they give birth. Now, you might notice things. I'm going to do this a few times. Okay. And it's doing a different bootstrap sample every time. So that's why it's slightly different trees every time. Okay. So one thing you might notice is that there are certain features that are kind of very important, like gives birth and warm-blooded. And those features kind of come up again and again as the most important features in the tree. Now, what's the problem here? The problem here is that we were trying to reduce the variance by averaging many different trees. But because some features are much more important than others, we end up with very highly correlated trees. For example, here we found that 2 of the bootstrap data sets actually gave us exactly the same tree, exactly the same splits. So both the first tree and the third tree are splitting first on gives birth and then on warm-blooded. So the trees are highly correlated. They don't give us as much reduction in variance as we would have liked. Normally, you reduce the variance by averaging, let's say, many different versions of the model. But if we're averaging many of the same versions of the model, we don't get any benefit. So to solve this, we can try a random forest instead. With a random forest, I'm going to put my mouse here so that you can see the other values we can pass. With a random forest, in addition to passing a bootstrap data set to each decision tree classifier that we train, we're also going to pass only a subset of features. So look at the default value of max features. So by default, for each split, it's only going to consider the square root of the total number of features. Okay, so at each particular split, it's going to randomly sample some of the features, and it's only allowed to split on those samples. So now if we look at the trees, okay, so you can see this time, let's say we split on aerial creature gives birth and hibernates in the first tree. In the second tree, we split on aquatic creature, aerial creature is warm-blooded, gives birth. In this one, we split on has legs, aquatic creature gives birth and hibernates. Here you can see there's a lot more variety in the trees. And every time we run it, again, we get very different trees. Actually, I'm not getting different trees. I think I probably have the same random seed set. But in general, you get very different trees with the random forest than you would for the bad classifiers. I think the random forest has some things to speed up computation, so it's not finding new trees. But these are much less correlated trees, so when you average their output, you get less variance. Okay, we mentioned another way to reduce the variance is with boosting. Let's remind ourselves the differences between the bagging method and the boosting method. So in the bagging method, we train many trees. Do we let each tree go as deep as it needs to until it classifies all the training samples with no error? Or do we usually limit the depth of the tree when we're bagging? I'm just going to add here to our existing tree. Okay, so we have bagging, we have boosting. With bagging, we generally do not limit depth. I mean, you could, but it's typically not what you do. What about with boosting? Do we let the tree grow, each individual tree grow until it classifies all the training samples, or do we limit depth? Okay, so with boosting, we usually limit the depth of the tree. We usually use very shallow trees for boosting. Okay, let's talk about other differences. In bagging, do we train the models in parallel, or do we need to do them sequentially? In other words, does tree 2 depend on what tree 1 was, or are they independent and could be built in parallel? Is there any dependence between the trees and the bag classifier? Okay, so the trees are independent trees. Train in parallel. And what about with boosting? Are the trees independent? Can they be trained in parallel? Okay, so in the boosted trees, they're trained sequentially because each tree depends on the previous tree in sequence. All right, what are some other differences? Is bagging meant to reduce variance or bias? Okay, so in bagging, the base estimator has high variance, and we try to reduce the variance. With boosting, does a base estimator, meaning each individual model, have high variance or high bias? Okay, so the base estimator, which is the individual tree that makes up the ensemble, has high bias. And we try to reduce the bias. Okay, any other major differences we forgot? I think that's basically it. Okay, so let's look at our boosted trees. We're going to use an algorithm called AdaBoost, which stands for adaptive boosting. This is the algorithm we described in class. And I'm going to fit an AdaBoost classifier with 3 trees. And remember, these are trained sequentially. And these are my individual trees. Now, notice that in the previous example, I let each tree grow until there's 0 entropy in the leaf nodes. Here, the default is for me to train what's called decision stumps, which are trees with only 1 split. Okay. So here, each tree has exactly 1 split. And in some cases, there is even still some entropy left in the leaf nodes. Okay, so you can see after my first split, well, I could say all of the animals that don't give birth are non-mammals, but among those that do give birth, well, 1/3 are non-mammals and 2/3 are mammals. But notice that in the next tree where I split on warm-blooded, now I'm able to classify all of my samples correctly. But we said that some of the samples that are warm-blooded are non-mammals, right? The penguin and the pigeon. So how am I able to classify correctly on being warm-blooded and have 0 error? Okay, so the answer lies in the weights that the classifier uses. So let's take a look at AdaBoost in a little more detail. I just want to point out here that, as you might expect, as you add more trees to the ensemble, you could see what the prediction accuracy is for the training set for as you add more trees. So this is a prediction accuracy for just the first tree. This is a prediction accuracy for the weighted output of the first 2 trees, and so on. Okay, there's a comment here that some samples are replaced. The AdaBoost algorithm is not using bootstrap samples. So it's training on the entire data set every time, but assigning different weights to different samples. So let's look at that more. All right. So here's my AdaBoost classifier. Now, sklearn has a perfectly good implementation of the AdaBoost classifier. But in this case, I implemented one by hand, basically from scratch, so we can see what it's doing. Okay, so here's the data we're going to use for our binary classification problem. And we have class labels -1 and 1. So the red samples are -1, the blue samples are 1. And now I'm going to select the base estimator and number of estimators. So I decided I'm going to run AdaBoost for 15 iterations. And for each iteration, I'm going to use a decision stump, which is a decision tree with a max depth of 1. So just, 1 split. All right, let's follow along in the algorithm shown here. Okay, So the first step is I let my weights be equal to 1 over n for every sample in the training set. So I'm going to initialize my weights to 1 over the size of the training set. Okay, here's my weights. I had 15 samples. So now my weights are all initialized to 1 over 15. Now I have my main loop. Okay, so this is the main loop. Let's just discuss for a moment. Okay, so in the main loop, I'm going to fit a tree. Okay, so let's say the tree for loop, for instance 0, the tree for instance 1, and so on. But I want to clarify that I'm going to fit a tree using weighted samples. What does it mean to fit a tree using weighted samples? Well, when I fit a tree using weighted samples, okay, so when it looks at the number of samples in each class, so previously I just gave each sample 1 vote. So if there were, let's say, 5 samples in one class, 10 samples in another class, each sample has 1 vote. So the 2 values are 5 and 10. And then I compute the entropy and decide whether to split based on the values 5 and 10. When I have weighted samples, then I give each sample a vote proportional to their weight. So here, for example, if the weight of each sample is 1 over 15, then when I compute how many negative samples and positive samples there are, I'm going to compute the sum of the weights of the negative samples and the sum of the weights of the positive samples. That's why I have, let's say, 1/3 and 2/3 here. And then I'm going to compute the entropy, or actually in this case, I use Gini index. I'm going to compute that based on those weighted sums. And then I'm going to, again, make that split decision based on the weighted sums. So here, when it says fit a tree, I want to clarify that we're fitting a tree based on the weighted samples. So I'm going to fit the tree of depth 1 in this case, using the weighted version of the training set. And then I'll get the predictions of the decision stem from the training data. Okay, so I'm going to loop over my list of decision tree instances. I'm going to fit the tree. And remember, I already specified that it has depth 1. I'll fit the tree. And notice that when I fit the tree, I'm passing a sample weight. And in the first iteration, my sample weight is just 1 over 15 for all of it. Then I'll get the predictions of the tree. Next, I'm going to compute the weighted accuracy of the stump. So the weighted error. I actually computed the accuracy of the stump just in the normal sense, even though it's not strictly required, but just because we want to be able to see later how each stump contributes. But this is not really part of the algorithm. The next part is to compute this weighted error metric. Where notice, okay, so this is just normalized by all the sum of the weights on the bottom. But for each sample, I'm adding the error. So whether or not there was an error on the sample times its weight. Okay. So in the first iteration, all the weights are the same. So I'm essentially just counting up how many samples had an error. But in the next iteration, some of the samples might have higher weights. We'll discuss in a moment why they might have higher weights. So if a sample had a higher weight, it's going to count more towards error. Okay. And the only samples that count towards the error are the ones that are misclassified. So this expression means it's 1 if the sample is misclassified, meaning y is not equal to the output of the model. And it's 0 if the sample is classified correctly. So I have this weighted error term, which depends on the weight of each sample and whether the sample was classified correctly. Next, I'm going to compute the coefficient. This is kind of an interesting function. Does anyone have any intuition for what this function looks like? Let's plot it. Okay, so I'm going to plot 1 minus x over x. And log 1 minus x. Okay. And perfect. We're looking at it from 0 to 1. Okay, let's look at it here. So let's look for a moment at how we're going to use this alpha coefficient. So we compute alpha coefficient from this function. And then we update the weights per sample. So in the next iteration, my new weights are going to be, okay, so previous weight, this should say, so my next iteration, my new weights are going to be previous weights times e to the exponent a. Okay, so alpha is an overall kind of weight for the entire decision stump in this iteration. And then whether or not the sample was misclassified. So which samples will have, okay, well, first let's look at alpha. Is alpha always positive or is it sometimes negative? Well, you can see it depends on the value of its argument. Right? So if the argument goes from 0 to 0.5, then it's always positive. If it goes from 0 to 1, it could be negative. Okay. What does it mean if the argument is negative? Let's go back here. So the argument is this expression here. Right? For alpha to be negative, we need this argument to be greater than 0.5. What does that mean if it's greater than 0.5? Well, let's see if we can get an intuition for that when we look at the actual trees. Okay, so we're going to update our weights here, where the weights increase if this expression is positive, meaning if our, okay, so the weights are updated if this is non-zero. So if this is non-zero, meaning the sample would misclassify it, then the weights increase. If this is 0, meaning the sample was classified correctly, then we have e to the 0 is 1. So then the weight is not updated. It's just equal to the weight from the previous iteration. And that's what we're doing here. So in each iteration, we're going to fit a decision stump, get its predictions. We're going to compute that weighted error term. And then we're going to compute the coefficient and update the weights. Let's do that. Okay, so we did this for 15 iterations just now. Now, the ensemble prediction at the end is going to be the weighted sum of all of those individual trees. So remember, our class labels are going to be +1, -1. At the end, I'm going to take the individual trees, take the prediction of each individual tree for each sample, and the sign of the output gives the predicted class. So let's imagine I didn't have the alpha term here. Then for a given x, the prediction would just be the more common class, right? Or, okay, not strictly the more common class, but it would be the sum of the predictions for let's say, each individual tree. So if many trees predicted positive class, then my prediction would be positive. If many trees predicted negative class, then my prediction would be negative. Now, what does the alpha term do? The alpha term weights the contribution of each individual tree. And remember, the alpha term depends on the error. If the error term is small, right? So if this error is small, should alpha be big or large? Should alpha be big or small? Okay, so if the error is very small, we set alpha to be large, and that means that this tree gets a bigger vote in determining the overall class label. So the better the tree does, the bigger alpha should be. Now, this is a binary classification problem, What if the error of the tree is essentially 50-50? The accuracy of the tree is about 50-50. What kind of contribution should it have to the overall decision? If the tree is basically a 50-50 classifier, then it doesn't really contribute any useful information. So we can give it a weight of essentially 0 in the overall decision. And then we'll have very little contribution or 0 contribution. What if the individual decision stump somehow has less than 50% accuracy? So what if it actually does worse than flipping a coin? How much should it contribute to the overall prediction? So negative contribution. If I have a tree that, let's say, always predicts negative when the tree output should be positive and vice versa, that's actually a really good tree, because all I need to do is take the output of the tree and flip the sign. If I have a tree that always predicts negative for positive samples and always predicts positive for negative samples, then I can just take the output of the tree, flip the sign, and it's a great tree. It's perfect. So if the tree accuracy is somehow less than 0.5, meaning the error is between 0.5 and 1, then I take the output of the tree and flip its sign, and I still count it as towards the overall prediction. So for a tree that's very good, has very small error, its weight towards the overall prediction will be high. For a tree that's about as good as a random classifier, its prediction weight will be very small. For a tree that kind of distinguishes between positive and negative classes, but somehow produces the wrong version of them, so it's a wrong class label, but most of the time, well, the more wrong it is, the more useful it is to me, because then I can just take its negative contribution. So I'm taking the sign of this sum, which is a weighted sum of the output of the individual trees. Exactly. So whatever the tree says, do the opposite. And this sign gives me the predicted class. And the magnitude tells me something about how confident I am in the ensemble. Why? Well, if there's a particular sample that many of the trees disagree on, so some of them predict negative, some of them predict positive, the magnitude of this will be small. If there is a sample where many of the trees predict the same thing, the magnitude of this is going to be large. So it gives us some estimate of how much agreement there is among the trees. Okay, so that was the entire algorithm. Now we're going to create a visualization of every stage. So I already ran the whole thing, and now I'm going to visualize it. And let's explain each of the plots in this visualization. Okay. All right, so we'll start with iteration 0. On the far side, I see the decision stump I produced in iteration 0. Okay, so this is the decision stump. I'm splitting on the value x1. I have two features here, x1 and x2. I'm splitting on whether or not x1 is less than 0.558. So I'm splitting right here. And notice that my Gini index is 0.5. I have 0.5 in each side. I have 0.5 in each class at the beginning. But after splitting on x1, I'm able to reduce that Gini index or measure of impurity a little bit, right? So the sum of the Gini index at the end is slightly better than it was at the beginning. And the overall classification accuracy is 0.66. Okay. Is this a really good decision tree? So it's not a great decision tree. The accuracy is 66%. On the other hand, it's better than flipping a coin. So I expect it can actually be useful for the overall prediction. My alpha is going to be 0.66. My error is 0.34. Okay. So the error was 0.34. So my alpha ends up somewhere in this positive range. Okay. After computing the predictions of the tree, I'm going to determine which samples are misclassified by the tree, and I'm going to increase their weight. So currently my tree is putting all of the samples in the left region as blue, okay? Because in the left region, the blue class has a slightly higher weight. Okay, so you can see in this region, the value for the blue class is slightly higher. That's a weighted value. And so this entire side is going to be classified as blue, which means all of the red samples here are misclassified. So I will increase their weight. This plot shows which samples which will have higher weight after this iteration concludes. Finally, let's look at the ensemble prediction after this iteration. Okay, so this is what the ensemble would predict. Now, currently the ensemble is just one tree, so it predicts exactly what this tree did. And the confidence I have in each sample is the same, just because, again, there is only one tree. So let's look at the next iteration. In the next iteration, I made the size of the points correspond to their weight. So notice that in the next iteration, these points, which were previously misclassified, now have their weight increased. So they're slightly bigger than the other points, and they're going to count more towards the overall decision boundary. And that's why we actually have a different split in this step, right? So we're splitting on exactly the same data, but the weight of the individual points is different. So that's why we have a different split. Okay, so in iteration 1, I split over here. Now my overall classification accuracy, not including the weights, is only 50-50. So we didn't really get too much out of this tree. So it's probably not going to improve our ensemble too much. And you can see that here. So the new ensemble prediction is going to be alpha times the prediction here, plus this alpha times the prediction here. And my weights did not change much, but notice that I now have more confidence in these samples. Sorry, my prediction didn't change, but now I have more confidence in these samples. Why do I have more confidence in these red samples on the side? Okay, so these are the only samples where both trees agree that these samples should be red. Okay. The top tree classifies these samples as red and these as blue. The second tree actually classifies all samples as red. So notice that in both cases, the value in the red class, which is the first class, is higher. So both trees classify these samples as red. On the other hand, for all of the other samples, the trees disagree. Right? So this tree classifies all of these samples as blue. This tree classifies all of these samples as red. Now, if they disagree, how did they decide that the ensemble prediction should be blue here? Okay, so the weight of the first trees is higher in the ensemble output because its value of alpha is higher. Its value of alpha is higher because its weighted error is smaller. So that's why the ensemble prediction prefers the prediction of the first tree to the prediction of the second tree. Okay, let's see which samples will increase in weight after iteration 1. So the blue samples in the middle were misclassified, so they'll increase in weight. Now they'll increase in weight relative to their previous weight, which means now we have 3 weights in the next iteration. These samples here, let me annotate. These samples here were never misclassified. So their weight is pretty small. On the other hand, these samples here were misclassified once, and these samples here were misclassified once. And so the weight of those samples will be higher than the ones that have never been misclassified. So let's see what happens in the next iteration. we have a different split, again, even though it's the same data. There's a question about how alpha is computed. Alpha is computed based on the weighted error. So it's not based on the unweighted accuracy of the tree. That's why this value here is the unweighted accuracy of the tree. This value here is alpha. That's why they're different. Okay, so in the next iteration, again, our weights are different, so our decision tree is different because it's making decisions based on the weighted sum of samples in each class. Okay. And in this iteration, I classify everything over here as red, everything over here as blue. Now, this has slightly better than random accuracy. So we expect that it might improve our ensemble prediction. And in fact, it does. So after this iteration, our ensemble prediction goes up to 0.82. Now, does our ensemble prediction always improve as we add more trees? Or can we say, does it always either improve or stay the same? So far it has. But as we, let's say, focus on more and more difficult examples, and let's say weight them more heavily, the overall unweighted accuracy will not necessarily improve. So we do have some cases where, let's say, the ensemble accuracy, unweighted accuracy might actually decrease from one iteration to the next. Here, for example, we could see that the ensemble prediction at iteration 4 was 90% accurate. At iteration 5, it actually went down to 68% accurate because it's focusing too much on some specific difficult examples. But eventually, as we kind of add more and more trees to our ensemble, on average, the accuracy tends to increase. And in this particular tree, we actually reached 100% prediction accuracy. Now, looking at this data set, would you expect to be able to classify correctly with a single decision stump? So a single decision stump should not be able to have perfect training accuracy. It can only make one split, right? But your ensemble output can be much more complicated than one split. In this part of the notebook, I showed you how the sklearn implementation actually produces exactly the same thing at every stage. So it's doing the same exact thing we did. But I'm just going to skip to the end and show you the decision boundary of the ensemble. Okay, so you could see the decision boundary of the ensemble is kind of like the weighted sum of all these decision regions. And so we actually end up with a kind of complex decision region, right? You could see it's not necessarily just like perfect squares. Okay, any questions on what we've covered so far? What does it split on? Can it split on multiple criteria? This particular tree was splitting on the Gini index. I'm not sure exactly what you mean by multiple criteria. So you have these two choices for the decision tree classifier and sklearn. Okay, if there are no more questions, we're going to go on to my favorite game, which is guess which model has more bias or variance. Does everyone like that game? All right, let's play. Now, some of these take a while to run, so I pre-ran this entire notebook. But we're going to use regression data from this very complicated looking function. So this is the data that we're going to use for each example. It's the same data for every example in this entire notebook. So this heavy blue line shows a true function. And the individual blue dots show individual training sets. Okay, so you could see the training samples follow the true function with some additive noise. And in each case, I'm going to fit two models to many independently drawn training sets. I'm going to do it 500 times for each model. And then I'm going to look at a few things. I'm going to look at the mean of all the model predictions. I'm going to look at the variance of the model predictions, so how much they vary around their mean. And then I'll look at individual error on test sample points and see if we can break down the mean squared error. Okay, so these are all pre-run. I'm going to try not to give the answer away. This is kind of a warm-up example because we looked at this last week. So remember our k nearest neighbor model. Which model has more bias and variance? Is it the one that uses one nearest neighbor or the one that uses 75 nearest neighbors? Okay, take a few more seconds to vote. Okay, so a small majority said that model B, which uses more neighbors, has more bias, and model A, which uses fewer neighbors, has more variance. So let's see if that's correct. All right, this is a little bit different from the bias variance plots we looked at before. So let's take a look. So we still have the individual training sample. That's just an example of a training sample as light blue dots. The heavy blue line shows a true function. Then I have like a cyan colored line. That's the mean of all the individual model predictions. And the red lines show, let's say, the first 20 models. Okay, so with which model does the cyan colored line, which is the blue line, most closely fit the cyan colored line, which is the mean line, more closely fit the true function, which is the blue line? With one nearest neighbors, the cyan line is exactly on top of the blue line. There's basically no bias at all. Remember, the bias is the difference between the true function and the mean prediction of many independently trained models. So one nearest neighbor was unbiased. What about 75 nearest neighbors? Does it fit the true function exactly? Okay, so you could see some differences here, here, and here. One way to think about this, I like to think of, let's say, the k nearest neighbors regression as like a moving average, right? So if you take a moving average using a small window, if you're familiar with like a moving average, if you take it using a small window, it's a little noisier, but fits the points much more closely. If you take it using a larger window, it forces it to be smoother. So that's exactly what we see here. If you use a prediction of 75 neighbors, you need to look farther and farther in the feature space to find them, right? So here, for example, I might have to take the average of all of these points in order to find my prediction here. So that has a smoothing effect, and that smoothing effect causes a bias. If I'm looking at a smooth version of the line, I can't track very fast changes in the line well at all. So that's why the example with more neighbors has more bias. Now, what about variance? Okay, so the red lines relative to the cyan line show the variance. We could see that the one nearest neighbor model has a lot of variance. So it varies a lot around the cyan colored line. The 75 nearest neighbor line does not. So the individual red lines are basically all exactly on top of the cyan colored line. There is very little variance around the mean. Okay, on the bottom, I'm showing, let's say for each individual point in the test set. So as X varies, how does the noise, bias, and variance vary? Okay, so the noise is the cyan line on the bottom. And there's basically, independent, identically generated noise for each test sample. So it's always around here. In the first example, the variance is also right around here. And intuitively, that kind of makes a lot of sense. When you're making your decision based on one neighbor, the variance is due to the noise in that neighbor. So it makes sense for the variance to be similar. And the bias here is this blue line down here, which is 0. So there's essentially no bias. And the overall error is the sum of all these 3 lines. So this was for the 1 nearest neighbor. Now let's look at the 75 nearest neighbor. So first of all, in this region, notice that the overall error is lower. And that's because the variance is lower. In this region, the variance green line is all the way down here. That's because the 75 nearest neighbor model, basically all of the model predictions are identical here because it's smoothing out all this noise of the data. Now, what happens as we move here? As we move here, we have increasing bias. So anytime there's like a sudden change in the data, the 75 nearest neighbor, which is like a moving average model, takes a while to catch up. And so we have bias anytime there's a sudden change in the data. So for these points, we have higher overall error every time there is kind of a sudden change, especially here, because of the bias of the 75 nearest neighbors. Okay, any questions? All right, that was our warm-up example, sorry. Let's look at our decision trees. So in our next pair of models, model A is a decision tree with a max depth of 5, and model B is a decision tree where the depths can be no greater than 100. Which model has more bias and which model has more variance? Okay, take about 10 more seconds to vote. All right, I think this is the first time I've ever done a round with 100% agreement. So let's see if everyone is right. Okay. Here I have the decision tree with depth constraint to 5. Here I have the decision tree with depth constraint to 100. Okay. So model A has more bias. Why does model A have more bias? Okay, so you can see here, if you look at the cyan line relative to the blue line, you could see that the cyan line is kind of flattened out here. It doesn't really follow the curves of the blue line. Why is that? So we remember that the decision tree will stratify the feature space into regions, right? And the more splits we have, so the greater the depth, the more splits we can allow, and the more regions we can create. So if we can only make, let's say, a small number of regions, every point in the region has to have the same prediction. So if, let's say, we can only divide by regions into this many regions, right? Everywhere within this region has the same prediction, which means it can't really increase here. On the other hand, when the depth is large, we can keep further dividing this until essentially every value has its own region. And then we can follow those curves more exactly. So that's what contributes to the bias of the decision tree with smaller depth. When the value is changing in, kind of quickly, then we'll have more bias. And we can see that here in the blue line down here. Now, what about the variance? So the variance of the decision tree with a large depth is much greater. We said that decision trees in particular are subject to high variance because depending on the draw of the training sample, if your root node, so the node at the very top ends up being different, it can change the entire tree. So the predictions can end up being very, very different. So decision trees with a large depth have much greater variance. And we could see that reflected here. So the variance line, which is this green line here, is up here. Whereas in the first case, where the depth was constrained, the variance is overall much lower. Ben has a question about the sample size. We're using 500 training samples for each training iteration and 100 test samples for the kind of plot at the bottom. And we're repeating each simulation 500 times. Okay, let's look at our next example. Our next example is a decision tree with and without pruning. Okay. So you might recall that we talked about pruning in our lecture on decision trees. Okay, so let's remind ourselves what we said about pruning. Okay, so in pruning, we reduce the size of the tree by kind of merging leaf nodes together. And we said that the iterative procedure we described was actually equivalent to minimizing this objective function. This is a squared error, plus a penalty for the size of the tree. So we have this alpha parameter, whereas alpha increases, the size of the tree in terms of number of leaf nodes decreases. Okay, so when alpha increases, the size of the tree decreases. With that in mind, let's see, which tree do you think will have more bias and more variance? Will it be the tree with small alpha or large alpha? Okay, so we're trying to minimize this expression. So if alpha is large, we require the tree to be smaller. Okay, take about 5 more seconds to vote. So conceptually, this is similar to the previous example. A smaller tree has a similar effect as smaller depth. When alpha, the tuning parameter, is large, you can kind of think of it as like a regularization penalty. The larger the value of alpha, the smaller the tree must be. And so the more bias the tree will have. On the other hand, increasing alpha decreases the variance. Okay, so that's exactly what we see here. The tree with a small value of alpha is allowed to grow bigger. And so it has more variance, but it's unbiased. The tree with a smaller value of alpha, the tree with a larger value of alpha, is not allowed to grow as big because there's a penalty on the tree size. And so this tree has more bias, but on the other hand, it has less variance. Okay, we talked about bagging and boosting as a way to control the bias variance trade-off. So suppose I have a decision tree and a bag decision tree. The bag decision tree is made up of an ensemble of 10 trees. Which one has more bias and more variance? You take about 10 more seconds to vote. Okay, so the answer to the first part, which has more bias, is actually a little bit tricky. Let's kind of work through it before we look at the example. In the first case, we have a decision tree. Okay, depending on the depth, it may have bias or may not have bias. In the second case, we have 10 decision trees, and we're taking their average. Now, the bias of the average depends on whether the individual trees are biased or not. So assuming that both trees have, let's say in model A and model B, the trees are allowed to grow to the same depth, is there anything about model B that would cause the trees there to have more or less bias than the trees in model A? So there's one small issue there, which is actually that we're not training on the identical data. We're training on bootstrap data. So it is theoretically possible for the bag trees to potentially have some extra bias because the individual trees might have somehow more bias because of the bootstrap data. But in practice, it hardly ever happens. So I would expect that both of these models will have similar bias. And that's what I find. Actually, in this case, they both have 0 bias. On the other hand, bagging is supposed to reduce the variance. Anytime we take the average of some quantity, we kind of smooth it out. And that's what we can see here. So the variance here is lower for the bag trees. And as a result, the overall error is lower as well. So the bag trees and the decision tree have similar bias in most cases. You can't necessarily say with 100% certainty that they'll always have the same bias, but in many cases, the bias is similar. But the bag trees reduce the variance. So it's kind of like a free way to reduce variance without affecting bias. Now, I said free, but it's not really free. The bag trees are not really, let's say, free because the runtime of training it is much larger. And the runtime of inference is also larger because I have 10 of them. Okay, let's look at the next example. So now we're looking at bag trees again, but we're varying the number of estimators. This takes like 10 minutes to run. So model A is an ensemble of 100 trees. Model B is an ensemble of 2 trees. Which one will have more bias and which will have more variance? Okay, take about 10 more seconds. Okay, so here we think that the 2 models will have similar bias, which based on our discussion just now makes sense. If the individual decision trees are the same, I would expect their average to also have similar bias. On the other hand, we expect the model with fewer trees to have more variance because the more trees, the more the variance is reduced. So let's see. So with 2 trees, we get, let's say, this reduction in variance relative to the original. With 100 trees, we get this reduction in variance relative to the original. Is this kind of difference surprising to anyone? So as we expected, the model with more trees has lower variance. But were you expecting a greater reduction in variance for 100 trees? So it's a little surprising. And this is unfortunately what actually happens. So the more trees you train, the more you reduce the variance, but you kind of have diminishing returns. So in order to keep reducing the variance even further, you need essentially an exponentially increasing number of trees, and it becomes very, very, very expensive. For example, this thing took, I believe, let's see, 146 seconds to run for 100 bag trees. Okay, let's look at another example using bag trees. So now we're going to vary the depth of the base estimator. Okay, so we said that with bag trees, we generally let the base estimator grow. But let's think about what might happen if we limit the depth of the base estimator. So I have model A is an ensemble of 10 trees, but each tree has a max depth of 5. Model B is an ensemble of 10 trees, and each has a max depth of 20. Take about 10 more seconds. All right. So when you take the average of many estimators, right, the result of the average depends on the individual estimators. So here we're taking an average of 10 estimators in each case, but we're changing the depth of the estimators, which means we're changing the bias and variance of the individual estimators. For model A, the individual trees will have more bias than the individual trees of model B because the depth is smaller. So we expect that the average of the biased trees in model A will have more bias than the average of the less biased trees in model B. And that's exactly what we see here. So model A has more bias if you look at the blue line on the bottom, and also if you look at the cyan line relative to the blue line on the top. Model A has more bias. On the other hand, if you take the average of many estimators, again, the variance of the average depends on the variance of the individual estimators. Okay, so taking the average reduces the overall variance, but you're reducing it relative to what it was in the first place. So here, the model A is taking the average of many trees with small variance. Model B is taking the average of many trees with large variance. So even though taking the average reduces the variance, we still have more variance for model B. And that's exactly what we see in the result. Okay, let's look at bag trees versus random forest. So you may recall when we looked at an example a moment ago, we said that the bag trees are often kind of correlated. And so they don't reduce the variance as much as we would like, because taking the average of many identical things doesn't actually reduce the variance. So as an alternative, we said we could use a random forest. Where at each split, you only consider a subset of parameters. And so the trees are less correlated. Which one do you think will have more bias and more variance? Okay, this is a tricky one. Take a few more seconds to vote. Okay, so class was very divided here. The truth is that this is a trick question. I'll explain why. Okay, so normally you expect the random forest to have less variance than the bag trees, because when you take the average of uncorrelated estimators, you reduce the variance more than if you take the average of correlated estimators. So the random forest tends to be more effective at reducing the variance. Okay. Now, with respect to bias, well, we said that one contribution to bias of the average relative to, let's say, in the plain decision tree is the bootstrapping, but both of them use the same bootstrap samples, so that doesn't make a difference. Then the other consideration is, does considering only a subset of features potentially affect the bias? And the answer is generally yes. So it's possible that the individual trees in the random forest might have more bias than the individual trees in the bag trees, because we're kind of restricting them to look at a subset of features in each split. So in general, you expect the random forest to have less variance, and it's possible that the random forest might have more bias, or it might not. It might be similar. In this case, though, I said it was a trick question. The reason it's a trick question is because there's only one feature. If there's only one feature, well, the bagged forest is considering one feature for each split. Sorry, the bag trees considers that one feature at each split. The random forest does exactly the same thing. There's no randomization of features in the random forest if there's only one feature to choose from. So these are actually exactly the same model. Yeah, sorry for the trick question. I just wanted to be able to talk about bias and variance of these without changing the whole data set. Okay, let's look at our next example. So we looked at a demo of AdaBoost. We're going to consider a single decision tree with max depth 5 and an ensemble of 10 trees with max depth 5 trained using AdaBoost adaptive boosting. Okay, you might want to remember what we said at the beginning of, let's say, between bagging and boosting, which one is designed to reduce bias, which one is designed to reduce variance. Might be helpful here. Okay, take 10 more seconds. Okay, I'm actually impressed. So we got this one right. This one's a little bit tricky to think about. Okay, so we know that the boosted classifier is designed to reduce the bias. We take many high bias classifiers, but we combine their output in a way that reduces the overall bias. And that's what we see here. It's a little tricky to see on the top, but you can see in some places, like here, for example, circle it. If you look here, for example, you can see the AdaBoost more closely follows the shape of the curve than the decision tree, than a single tree. The AdaBoost classifier is less biased. And you can see that also down here. So the blue line is lower for AdaBoost. Now, even though the primary way it works is to reduce the bias, it also has a nice side effect of reducing the variance as well. Because even though your main objective is to reduce the bias by combining many bias estimators, anytime you average the output of many estimators, you reduce your reliance on any individual noisy training sample. And here we're actually kind of averaging many kind of slightly different estimators because each one is trained on a different set of weights. So when we take the average of all of those, we reduce the variance as well. And so here you can see that the green line, which represents the variance, is smaller in the AdaBoost case. So AdaBoost reduced both the variance and the bias. Okay, we'll look a little more at AdaBoost. What do we think is the effect of number of iterations? This is also kind of a tricky one to think about. Okay, take a couple more seconds. Okay. So model A has more bias. That's kind of easy to think about. So we're taking many biased estimators, and every time we add another estimator, we're able to kind of reduce the bias a little bit more. So the bias of an ensemble tends to decrease as we add more iterations, more trees. The variance is a little more complicated to think about. Now, in this case, they happen to have identical variance. In a general sense, so it's possible for boosted trees to kind of overfit and have higher variance. If you have too many trees, especially if the data is very noisy, you can end up kind of fitting to specific training examples, having a very complex decision region, and overfitting and increasing the variance that way. On the other hand, you have this competing effect on variance, which is as you increase the number of iterations, you're taking the average of many more contributions. So increasing iterations, on the other hand, can increase the risk of overfitting. But on the one hand, it averages more elements, and that reduces the variance. So in practice, it's possible for an AdaBoost classifier to overfit, but it's very rarely a concern because we have this balancing effect on the risk of overfitting. Okay, one more example, and then we'll start looking at SVMs. Okay, so here we're having an AdaBoost ensemble with 50 estimators in each case. But in the first case, I'm using trees with max depth of 3. In the second case, I'm using trees with a max depth of 30. Take about 10 more seconds. Okay, another unanimous decision. So with any ensemble, the bias and variance of the ensemble depends on the bias and variance of the individual trees. Even though we expect AdaBoost to probably reduce the bias and maybe also reduce the variance, it's still relative to whatever trees you're using originally. So when you have the max depth 3, the original trees have more bias, and so the ensemble has more bias. That's why the blue line is larger down here. With the trees of depth 30, the individual trees have more variance, as you can see in the green line, and so the ensemble also has more variance. So everyone got that one right. Okay. All right, any questions on this notebook? Okay, let's look at SVMs. We haven't even touched SVMs yet. Okay, we're going to take a quick look at that, SVMs and maximal margin classifiers. So we're going to be thinking about data that is linearly separable at first. Okay, so here I have two classes, binary classification problem. I have red points and yellow points. And we know that we can have many possible separating hyperplanes that divide these classes perfectly. And each separating hyperplane would have a different result. So for example, if I would add this new test point with an X, some of the separating hyperplanes would classify on them on the red side, some on the yellow side. We know that one way to choose a line is to think about, let's say for each potential hyperplane, what is the distance between points of opposite classes? Right? So kind of take a rectangle and squeeze a rectangle in there so that it fills up the space between opposite classes. And then choose a hyperplane that has the widest slab. So here you can see if you want to maximize the width of that rectangle, this line is obviously the best. So this is a maximal margin classifier. Now let's use it to fit that data we described up there. So I'm going to fit a support vector classifier, and I'm plotting it, and I'm also plotting the support vectors with a circle and the margin that separates the classes. Okay. Now these points are known as support vectors because the fit depends only on the hyperplane and the margin depend only on the support vectors. So notice that, let's say if we add more points that are not support vectors, like let's say if we go from 60 points to 120 points, we've doubled the number of training samples, but we haven't changed the hyperplane or the margin at all. And you can kind of play around with that and see, right? If we add more points and they are support vectors, meaning they end up either within or on what was previously the margin, then the hyperplane moves or the margin moves. But if we add points that are not support vectors, it has no effect on the margin. So only the addition of points in this region will affect the model. Now that works fine if your data is linearly separable, but your data is not always linearly separable, as shown here. So in that case, we can use a support vector classifier that has a soft margin. With a soft margin, we allow some of these points to be inside the margin subject to some budget. Okay. Now we're going to describe that budget in terms of this tuning parameter C, which is a parameter in the sklearn implementation, where C weights kind of this sum, where this sum is, let's say, how many points were over the margin and by how much. Okay. The greater the value of C, the more the, let's say, margin violators penalize the overall objective. So if C is large, then the margin violators have a stronger effect on the overall objective, which means we need a narrow margin with fewer margin violators. If C is small, it means our margin is softer. We don't care as much about the margin violators. And so we can have a wider margin. Okay, so here's an example of this data classified with a support vector classifier. Here, C is large, which means that each margin violator penalizes the overall objective function a lot. So the margin must be very small. Here, C is much smaller, which means that the margin violators have much less contribution to the overall objective. And so we can allow many margin violators and the overall margin of white. Okay, we have one more round of our game. Okay, so I have model A and model B for this data set. One of them is a support vector classifier with a small value of C. And one is a support vector classifier with a large value of C. Which one has more bias? Which one has more variance? I feel like it kind of helps to think about this in the extreme case. So in the very extreme case, if you let C be very, very small, then you essentially allow all the points to be in the margin. Take like 5 more seconds to vote. Or as many seconds then. Okay, now it's it. Okay. So model A, which has a smaller value of C, which means it tolerates a wider margin. Model A has more bias but less variance. Has less variance because it's less dependent on the individual draw of training samples because it allows so many support vectors. On the other hand, because we allow so many support vectors, we're not really kind of fitting the data as well. And so we end up with higher bias. Model B, which tolerates fewer support vectors, has less bias. We're kind of fitting the data more well because we're creating a separating hyperplane with fewer violations. On the other hand, there's more variance because it's much more subject to the individual draw of training samples. Okay, we're not going to do this part today. We'll do that next week. But I want to show one more thing about the support vector classifier. So we previously did an example with handwritten digits with logistic regression. And now I want to kind of take a step back and look at the same classification problem using multiple methods. So let's remind ourselves, I believe I pre-ran this one also. No, I didn't. Okay, I'm going to pre-run this one. Okay, so we're going to load in the data set again. Give it a second. It's the same data set we worked with before. So 784 features, 70,000 samples. And we're going to split it into training and test sets that are smaller because this is just for demo purposes. And we're also going to scale the data so that the range of each point is 0 to 1. Okay, let's give it a second to finish fetching the data. Okay, while it's fetching the data. So we're going to look at each of the classification techniques in terms of a few things. First of all, we'll look at the classification accuracy, but we want to kind of take that with a grain of salt because we're not going to do any hyperparameter tuning. So it's possible that we could improve the accuracy of any of these with tuning hyperparameters. Then we'll look at the time it takes to train the model and the inference time. And we'll look at the interpretability of the model too. So how can we use a model to kind of interpret how it arrived at the decision? Okay, logistic regression. It took about 2 seconds to train, and it takes about, let's say, on the order of 10 milliseconds to make a prediction, so inference. Okay, so let's keep that in mind as like a baseline against which we compare the rest. A couple of seconds to train, and some tens of milliseconds for inference. And it did pretty well, so above 90% accuracy, but not great. Now, for each of these classifiers, we're going to look more closely at the samples it classified incorrectly to try and figure out why. And so we'll look at a few random samples here. We know for the logistic regression, we can kind of interpret the results by comparing, let's say, the feature values, so X for each sample, times the weights for each feature for each of the classes. So here, for example, we can see in this example, this is actually a 7, but it was predicted as 2. And if we look at this, right, we can start to understand why it was classified the way it was. So we can see that the positive, the blue points show the points where, let's say, the 2 class considers it more likely that you belong to that class if there was writing in that area. Okay. So here we can see there's plenty of writing in the area that the 2 class considers a positive contribution. And there isn't really any writing in the area that the 2 class considers a negative contribution. So this makes it more likely that we belong to the 2 class. On the other hand, looking at the 7 class, so down here, we can see this sample has plenty of writing in the area that belongs to the 7 class. So here. It also does have some writing in the middle here, which is negatively associated with belonging to the 7 class. And we can do something similar for any of the examples, so we can kind of understand why they were categorized as they were. Okay, let's look at the k nearest neighbors. So fitting time was similar to the logistic regression, a couple of seconds. But the prediction time, the inference time, was much longer. Is that what we expect? Okay, so absolutely. So the inference time for the logistic regression scales with only the number of features. But for the k nearest neighbor, it scales with the number of features and the number of training samples. So this takes much, much longer to do inference. The accuracy is reasonable. Now, generally, k nearest neighbors is not great for images, but in this case, it's like a lower dimension image, so it's not too terrible. And again, we can look at some of the misclassified samples and kind of understand why it made the decisions it did. Okay, so looking at these samples, in the top row here, we're showing a sample that was misclassified. We're showing the true label and the predicted label. And then we're looking at the 3 points that were considered its nearest neighbors and their labels. Okay, so let's say looking at this example, this is actually a 2, but it was predicted as a 7. And looking at the nearest neighbors and their distances, it's very easy to see that, yes, these are in fact very similar examples. And we can understand why it was predicted as a 7. Now, in some cases, it's less easy to see, right? Here, for example, So this is a 5. It was predicted as a 1, just because the nearest neighbors are these 3. And these 3 samples each have a different class label, so we'll randomly choose one. So we chose this one. Now, in this case, it's not so easy to see how similar this is to these 3 other ones. It doesn't really look that similar. And that's because we know that, these per pixel-wise distance metrics are not really good measures of visual perceptual similarity. So with the k nearest neighbors, we can see why it made the decisions it did. We can look at what were the nearest neighbors and how close they were. But sometimes a distance metric is not a good fit for, let's say, image data. Okay, next we'll look at our decision tree classifier. It takes a little bit longer to train, a few seconds also. But again, it's very quick to do actual inference. Okay, so it's on order of the logistic regression. The inference time of the decision tree depends on how deep the tree is, so how many comparisons you have to make. So it doesn't scale with the number of training samples or anything like that. Okay. On the other hand, it did a terrible job. So accuracy is only 80%. Conceptually, this makes a lot of sense, because if you think about like having to, let's say, make a splitting decision on every individual pixel in the image, or every individual horizontal and vertical line in the image, every individual pixel in the image, it kind of makes a lot of sense that it's not going to do a very good job. Now, in terms of interpretability, usually the decision trees are pretty interpretable, but in this case, it's going to be a huge tree. Now, we can limit ourselves to a tree of depth 4 for, let's say, the plotting purposes. So even though this is a very large tree, we can look at a subset of this. The default plotting method does not work well at all with the big tree, but this alternative plotting method does. So we're looking at only, let's say, the first 4 rows of the tree. And we could see it's doing exactly what we anticipated. It's splitting on the value of individual pixels. So essentially, is there writing in this pixel or not? So we can understand you need a lot of splits and an extremely large tree to make decisions based on whether there is writing in individual pixels or not. And we're also kind of looking at these interactions. So let's say a sample might be a 1 if there is writing in, okay, so a sample might be considered a 1 if there is writing in this pixel, then writing in this pixel, then writing in this pixel, but no writing in this pixel, and this pixel, and this pixel. So it has those built-in interactions, but it's not very effective to split on individual pixels. Now, in terms of interpretability, so decision trees are usually interpretable. This tree is absolutely not interpretable. Doesn't really tell us anything when we look at splitting on individual pixels. Decision trees can also usually give us some measure of feature importance. We can compute feature importance for this tree, but again, it's just telling us which pixels appear more often in the tree. So, okay, great. The pixels in the middle of the image are more important. The ones around the outside are not important, but it's not very interpretable. Now, if we train an ensemble, it gets even less interpretable. Also, the training time gets longer. So training an ensemble takes longer because we need to train more and more trees. So the training time and the prediction time tends to scale with the number of trees, as well as whatever it's scaled with originally. On the other hand, the ensemble does a much better job. Is the ensemble interpretable? Absolutely 100% not. So there's really no reasonable way to look at 100 extremely deep trees and say, oh, this is why I made the decision. Okay, the most interesting of these examples is the support vector classifier. So it takes on order of tens of seconds to train. So it's slower than the logistic regression, but a little faster than, let's say, some of the ensemble methods. And the prediction time is, okay, let's compare the prediction time to k nearest neighbors. So the prediction time of the support vector classifier is, let's say, 10 seconds. For k nearest neighbors, it's about a minute. And so we can think of the support vector classifier as looking at the support vectors as nearest neighbors, potential nearest neighbors, and making the decision based on that. So the inference time doesn't really scale with the number of training samples, but it does scale with the number of support vectors. Okay, the accuracy is about 92%. But let's look at some of the misclassified samples. Okay. So before we do that, we're going to look at the support vectors directly. So here are some of the support vectors. Now, do these support vectors look like kind of easy samples to classify or difficult samples to classify? Do they look like, similar on average in terms of difficulty, more difficult or less difficult? So these look like pretty difficult samples, right? Like this 7, I would have classified that as a 1. This 8 is barely legible. This 3 is missing a stroke. So the support vectors tend to be kind of difficult samples. Why is that? Well, these are the samples that are either near or even across that separating hyperplane, right? Which tends to be the ones that are kind of more difficult. Okay. And we can see that if we would, let's say, train our logistic regression on the entire data set, we got about like 93% accuracy. But a logistic regression trained on the support vectors only does about 70%. Sorry, not trained. The logistic regression we previously trained only has an accuracy about 75% on the support vectors. Now, we're going to look more into this like nearest neighbor interpretation of the support vector classifier, but it's easier to understand for a binary classification problem. So we're going to restrict ourselves to a binary classification problem where we're going to train our support vector classifier to classify digits that's either 5 or 6. Okay. So we did pretty well. And we're going to pick a random misclassified sample to explore in depth. Okay, so this sample is actually a 6. It was misclassified as a 5. Now, to see how it made its decision, we're going to compute this value. Okay, so remember we said the solutions of the support vector classifier are right here. So if we have a new sample to classify, we're going to compute the sign of this value. So the intercept plus the alpha coefficients, these are the Lagrange coefficients, times the class label, which is positive or negative, times the dot product of the test sample and all of the support vectors, right? Because we know that alpha will be 0 for any point that's not a support vector. So we're going to try and look at this quantity here for the support vectors in our example and our misclassified test sample. Okay. So first we get the list of support vectors. When we get the list of support vectors, we get one long array. This is an array of indices. And then we get an array that tells us the number of support vectors in each class. So of this list of 183 support vector indices, the first 89 belong to one class, the next 94 belong to the other class. So we'll split our indices into, let's say, positive class and negative class by taking, let's say, the first 89 and then the next 94 examples. And then we'll use that to get the alpha coefficients. Now we have the alpha coefficients. Let's do a little sanity check here. Okay, so we know that the dual support vector classifier problem looks like this. The alpha coefficients are required to each individually be less than C. In this example, C was 10. Are my alpha coefficients less than C? So we can see that they're all individually definitely less than C. Most of them are actually less than 1. Okay, and we also have a constraint that the sum of the alpha times y's should be equal to 0, which basically means that this budget should be equally distributed on both sides of the separating hyperplane. And so we'll do that sanity check too, and we see that constraint is also satisfied. Okay, now we're going to compute the dot product of the support vector and the test sample for each support vector. Okay, so this is the test sample. we're going to take the dot product of this and each support vector. And we could think of that dot product as like a similarity value. Right? So let's say all these black points are 0. If we take the dot product of this and another sample with, let's say, 0 elements in the same pixels, right? You multiply all those zeros or very small values, you get zeros. If they have large value in the same pixels, you multiply those large values, and the overall result is large. So the dot product is bigger if the two samples are more similar. So we think of it as like a similarity measure. So we're going to compute those similarities now for every support vector. Now we'll look at them separately for each class, okay? Just because we happen to have that separately in 2 separate arrays. So this is the sum for, let's say, the positive class, for the negative class. And this is the sum of this quantity for the positive class. We're going to add those two together, also add the intercept. And the sign of this value, the sign of this quantity here, tells us whether it belongs to the positive class or the negative class. Okay, so here it's negative, and that's why the sample is interpreted as belonging to the negative class, which is a 5. Now, to understand it, we'll look at that those specific support vectors that mattered most in making the decision. So we can think of the support vector classifier as like a weighted nearest neighbor. Okay. So here, the weight depends on 2 things. So first of all, we're considering all of the support vectors as neighbors. Okay. So we're taking the vote from, okay, so this, let me get my pen. Okay, so this yi is the vote of each individual neighbor or support vector. And then the weight of the support vector depends on alpha and xi dot xt. Okay. So we're taking a weighted nearest neighbor where the weight depends on 2 things. Okay. First, it depends on alpha. What is alpha determined by? Alpha is determined by how much of a margin violator the particular support vector is. If a point doesn't violate the margin at all, alpha is 0. If a point is farther over the margin or even over the hyperplane, alpha is larger. So we more heavily weight the difficult samples. You can think of it as like concentrating on difficult samples. We also weight by how similar we are to the support vector. So it's like a weighted nearest neighbor where we're weighting difficult samples more heavily, and we're also weighting more similar samples more heavily. So with that in mind, let's first look at our test sample and the samples with the highest value of alpha. So the samples with the highest value of alpha are the ones that are, let's say, the most important support vectors in the overall decision, because these are the ones that are farthest over the margin. So here is our test sample and the most important support vectors in the 5 class. Okay. Can we see why these are kind of farther over the margin? Okay, so these are definitely very difficult samples, right? I would never have classified this as a 5. I would have said it was a 6. Same with the samples in the 6th class, right? These have the highest value of alpha among the support vectors because they're farther over the margin, because they're difficult to classify. So these will count more in the decision of whether it's a 5 or a 6. Similarly, we can look at the ones that are considered most similar. So these are the support vectors for which the dot product of the support vector and the test sample is greatest. We could think of these as most similar. Do these look pretty similar to the test sample? So these are the 5s that are most similar among the support vectors. And these are the 6s that are most similar among the support vectors. And we could see these are pretty similar examples. So this is our interpretation of the support vector classifier as like a weighted nearest neighbor. When you first learn about the support vector classifier, it seems most similar to a logistic regression because you're learning a linear separating hyperplane. But with this interpretation, we see that it's actually more like a kind of weightest nearest neighbor, where you're weighting samples more heavily if they're difficult to classify or if they're more similar to yourself. Okay, it's almost 11. That's all I had for today. Are there any questions? All right, great. Thanks a lot.